DBSCAN. Clusters just like a person can. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about clustering with DBSCAN, and it's going to be clearly explained. Now, imagine we collected weight and height measurements from a bunch of people. And we plotted the people on a two-dimensional graph like this, where we have weight on the x-axis, the first dimension, and height on the y-axis, the second dimension. By eye, we can see two different clusters, by identifying two different, but relatively dense, clumps of people. In contrast, these people that are far from everyone else look a little bit like outliers. So, by eye, clustering this data is pretty easy. However, because these clusters are nested, meaning the green cluster wraps around the blue cluster, a relatively standard clustering method, like k-means clustering, might have difficulty identifying these two clusters. Instead, because of the nesting, a simple clustering method might get something weird like this, where these points are assigned to the blue cluster even though they look like they belong to the green cluster. So we need a clustering algorithm that can handle nested clusters. Also, remember, this two-dimensional graph only uses weight and height data. But if we wanted to include each person's age, we would have to add a third axis. And now our graph is three-dimensional. Drawing a three-dimensional graph on a two-dimensional computer screen is awkward, but possible. However, if we wanted to include 4 or more features, we'd need to draw a 4 or more dimensional graph, and that's not possible. And if we can't draw and look at a 4 or more dimensional graph, then we need a way to identify nested clusters that we cannot see by eye. The good news is that there are clustering algorithms that can identify nested clusters in high dimensions. One of these algorithms is called DBSCAN, and that's what we'll talk about today. So let's go back to the original two-dimensional graph and see how DBSCAN tries to mimic what we can easily do by eye. Now, remember, by eye, we identify clusters by the densities of the points. Clusters are in high-density regions, and outliers tend to be in low-density regions. So let's see how DBSCAN uses the densities of the points to identify these two clusters. Bam! Now, starting with the raw, unclustered data, the first thing we can do is count the number of points close to each point. For example, if we start with this red point, and we draw an orange circle around it, then we can see that the orange circle overlaps, at least partially, 8 other points. So the red point is close to 8 other points. Note, the radius of the orange circle is user-defined, so when using DBSCAN, you may need to fiddle around with this parameter. Now, this red point is close to 5 other points because the orange circle overlaps, at least partially, 5 other points. This red point is close to 6 other points, and this red point is close to 7 other points. This red point is only close to 2 other points, and this red point is not close to any other point because the orange circle does not overlap anything else. Likewise, for all the remaining points, we count the number of close points. Now, in this example, we will define a core point to be one that is close to at least 4 other points. Note, the number of close points for a core point is user-defined, so, when using DBSCAN, you might need to fiddle with this parameter as well. Anyway, these 4 points are some of the core points because their orange circles overlap at least 4 other points. Hooray! But neither of these points are core points because their orange circles do not overlap 4 or more other points. Wah wah. Ultimately, we can call all of these red points core points because they are all close to 4 or more other points. And the remaining points are non-core. Now we randomly pick a core point and assign it to the first cluster. Next, the core points that are close to the first cluster, meaning they overlap the orange circle, are all added to the first cluster. Then, the core points that are close to the growing first cluster join it and extend it to other core points that are close by. Here we see 2 core points and 1 non-core point that are all close to the growing first cluster. And at this point, we only add the core points to the first cluster. That said, eventually we will add this non-core point, but right now we are only adding core points. Ultimately, all of the core points that are close to the growing first cluster are added to it and then used to extend it further. Bam! Note, at this point, every single point in the first cluster is a core point. And because we can no longer add any more core points to the first cluster, we add all of the non-core points that are close to the core points to the first cluster. For example, this point, which is a non-core point, is close to a core point in the first cluster. So we add it to the first cluster. However, because this is not a core point, we do not use it to extend the first cluster any further. That means that this other non-core point, which is close to the non-core point that was just made part of the first cluster, will not be added to the first cluster because it is not close to a core point. So, unlike core points, non-core points can only join a cluster. They cannot extend it further. Now we add all of the non-core points that are close to core points in the first cluster to the first cluster. And now we are done creating the first cluster. Double bam! To summarize how the first cluster was formed, we picked a random core point and it started the first cluster. Then, neighboring core points joined and extended the first cluster. And non-core points only joined the first cluster. Bam! Now, because none of these core points are close to the first cluster, they form a new second cluster because they are close to each other. And the non-core points that are close to the second cluster are added to it. Lastly, because all of the core points have been assigned to a cluster, we're done making new clusters. And any remaining non-core points that are not close to core points in either cluster are not added to clusters and called outliers. And that is how the DBSCAN algorithm works. Triple bam! Note, as we just saw, clusters are created sequentially. That means if we had a non-core point close to both clusters, then, when we built the first cluster, we would add this non-core point to the first cluster because it is close to a core point, along with all of the other non-core points that were close. And now that this point is part of the first cluster, it is no longer eligible to be in any other cluster. Small bam. Now it's time for some shameless self-promotion. If you want to review statistics and machine learning offline, check out the StatQuest study guides at statquest.org. There's something for everyone. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing to my Patreon campaign, becoming a channel member, buying 1 or 2 of my original songs, or a t-shirt or a hoodie, or just donate. The links are in the description below. Alright, until next time, Quest on!